Imagine unboxing this, brand new $10,000 piece of enterprise networking hardware.
Oh, yeah, the really heavy stuff.
Right. You rack it, you plug it into the power, you snap in all the Ethernet cables, and then absolutely nothing happens.
Just blinking lights.
Exactly. The fans spin up, but it is effectively a completely deaf, dumb, and highly vulnerable paperweight. Bringing that machine to life requires a very specific, deliberate digital choreography. So our mission for today's deep dive is to uncover that hidden choreography for you.
It's a great mission.
We're looking at how the true workhorses of the internet, routers, are built from an absolute blank slate into the devices that literally run the world.
It really is a phenomenal transformation to look at from the inside out. We are grounding today's discussion in the architectural concepts taught in enterprise networking, specifically drawing on foundational Cisco configuration modules like those from Sewella Technical Community College.
Right.
And what becomes apparent very quickly in those ITech 1210 notes is that a router doesn't just figure things out on its own. It requires a human to orchestrate every single capability.
Yeah, the underlying premise in enterprise networking, it basically treats routing packets of data across the world exactly like a relay race.
That's a really good way to put it.
The data is the baton, right, being passed from one runner to the next. But the catch is that an out-of-the-box router cannot just show up to the track and run its leg of the race. It doesn't even know what a track is.
No, it's totally lost.
So today, you and I are acting as the coach. We are taking this blank slate, giving it an identity, and getting our runner ready for the track.
And before a runner can step onto the field, they need, a uniform, a locker, and they need to know who they are. Because a brand new router is essentially a vulnerable black box.
Completely exposed.
Exactly. Putting armor around it immediately is the absolute first priority. Without that, it's a massive liability to the entire network infrastructure.
Okay, let's unpack this. Because it really parallels buying a new smartphone.
How so?
Well, when you pull a phone out of the box, the very first things you do are give it a custom name and set up a lock screen passcode so a stranger can't just, pick it up and alter your life.
Right.
But I imagine in the enterprise space, the stakes are a little bit higher than someone posting a fake status update on your social media.
Oh, massively higher. Consider the blast radius, right? If someone accesses a personal phone, you lose some data.
Yeah.
But if an unauthorized user accesses the privileged EXEC mode on a core enterprise router,
Which is the main control center, right?
yeah, the highest level of access, if they get in there, they can reroute traffic, wipe configurations, or take down the communications of an entire corporate campus or even the city.
Wow.
That is why the very first action an engineer takes is assigning a unique identity using the hostname command.
Because out of the box, they're all just called the same thing.
Exactly. By default, every Cisco device is just named router.
Just router.
It's just router. And when you manage 10,000 devices across a global network, staring at a generic prompt is exactly how catastrophic mistakes happen. You think you're working on the test lab, but you're actually on the live production router.
Oh, that sounds like a nightmare.
It is. So typing hostname R1, for instance, changes the command line prompt instantly. It anchors the engineer in that specific machine's environment.
And once it knows it's R1, you have to actually build the vault doors around it.
The main vault door protects that privileged EXEC mode we just talked about. This is the mode where you hold the keys to the kingdom. Engineers lock this down using the enable secret command.
Enable secret. Sounds very dramatic.
It kind of is. And what happens under the hood here is critical. Older systems used basic passwords that were just easily readable text. But enable secret relies on cryptographic hashing.
So it scrambles it.
Exactly. It takes the password you type, runs it through a complex mathematical algorithm, like MD5 or SHA, and stores only the resulting complex string of gibberish.
Meaning, even if someone gets their hands on the configuration file, they can't see what the actual password is.
Precisely. Even if an attacker steals the file, they cannot easily reverse engineer the original password from that hash.
Okay, so that secures the deepest level of the machine, the core, but you still have to protect the actual pathways used to reach the machine in the first place, right? Like the physical and virtual doors.
Right. The physical door is the local console port. To use that, you literally have to stand in the freezing data center with a laptop and plug a serial cable directly into the router.
I've seen guys doing that. It does not look comfortable.
No, it's not. And that port gets locked down with its own specific console password. But modern networks are mostly managed remotely, which means securing the virtual doors.
And those are the, what are they called?
The VTY lines, or virtual teletype lines, this is how you access the device over the network using protocols like SSH or Telnet.
Okay, now setting all these different passwords brings up an interesting vulnerability that I want to ask about.
Sure, go ahead.
If the enable secret master lock is heavily hashed, like you said, what happens to the passwords on those console and VTY lines? Are they just sitting in the configuration file in plain text for anyone to read over an engineer's shoulder?
Well, by default, yes. They are completely exposed in plain text.
Wait, really? That seems like a massive oversight.
It's a legacy thing.
Mm.
But to fix that, engineers deploy the service password encryption command. This acts as a sort of blanket over the config file. But it is vital to understand the nuance here.
So what's the catch?
This command uses a very weak form of encryption called a Type 7 cipher. It is not designed to withstand a dedicated cryptographic attack.
So a hacker could crack it pretty easily.
Very easily. It is purely designed to prevent shoulder surfing. If a junior technician is just walking by and looking at the screen, they see scrambled text instead of the actual console password.
Ah, I see. It's a deterrent, not a fortress.
Exactly, which is exactly why Enable Secret uses much stronger hashing for the real vault.
That makes perfect sense. You use the heavy vault door for the master controls and just kind of frosted glass for the side doors to keep casual snoops out.
Perfect analogy.
But there is also a completely non-technical layer of armor applied at this stage, right? The legal warning.
Ah, yes, the message of the day, or banner mot command. Engineers configure a text warning bracketed by delimiters.
Delimiters, like symbols.
Yeah, like a hashtag at the beginning and end of the message.
Mm.
And this warning displays the moment anyone attempts a login.
What does it usually say?
Usually something intimidating like, unauthorized access is strictly prohibited and monitored.
Just to scare them off.
Partly, but it's mostly legal cover. In many jurisdictions, if you do not explicitly state that the system is private and restricted, prosecuting a trespasser who breaks in becomes significantly harder.
Okay, so the identity is set, the cryptographic locks are in place, the virtual doors are secured, and the no trespassing sign is staked in the front lawn.
It's locked down tight.
But all of this work happens in volatile memory, right? If the facility loses power, doesn't the router wake up with total amnesia?
It does. Routers use RAM for their active running configuration because RAM is incredibly fast. That speed allows the device to process millions of packets a second.
But RAM is temporary.
Right, it forgets everything the moment the electricity stops. So to make the digital fortress permanent, the engineer has to deliberately copy that configuration from volatile RAM into NVRAM, which is non-volatile RAM.
So it's a specific command to do that.
Yes, copy running config, startup config. It is basically the network equivalent of hitting save on a massive document you've been working on for hours.
Yeah, you definitely don't want to forget that one.
Absolutely not.
So our runner has their uniform, the locker is secure, and they remember who they are even if the lights go out. But they are still sitting totally isolated in the locker room. We need to actually plug the router into the track so it can receive data.
Time to wake up the ports.
And it's wild to me that enterprise routers ship with their interfaces completely disabled out of the box. I mean, in the consumer space, you plug a cable into a home router and it just instantly figures it out. It's plug and play.
Yeah, very different philosophy there.
So why do enterprise devices default to a state of being administratively down?
Because consumer devices prioritize convenience, while enterprise devices prioritize absolute control. A single enterprise router might connect dozens of highly complex networks.
So if it just woke up on its own, it could cause chaos.
Total chaos. If those ports were live by default, plugging in a cable could instantly introduce a broadcast storm that overwhelms the whole network. Or worse, it could accidentally connect a highly secure database subnet to a public-facing lobby network before you've set up the firewalls.
Oh man, yeah, that would be bad. So we have to explicitly invite the data in.
Precisely, by diving into the specific interface configuration mode.
How's that look in practice?
We'll take a standard branch router, like the Cisco ISR 4321 from the notes. It usually has a couple of gigabit Ethernet interfaces. The administrator selects one, say gigabit 00, and assigns it an identity on the network using an IP address and a subnet mask.
And are we talking IPv4 or IPv6 here?
In today's hybrid environments, it almost always means assigning an IPv4 address and a modern IPv6 address simultaneously.
And once it has an address on the network, how do we actually wake the port up?
You use the no shutdown command.
Yeah.
It essentially removes the administrative block that was keeping the port asleep.
I've always loved that phrasing. It's not turn on, it's just, hey, don't be shut down.
It's very literal.
It's like flipping the main breaker switch in a house to finally send electricity to a room you just meticulously wired.
What's fascinating here is that typing no shutdown only flips the breaker on your side of the house.
What do you mean?
Well, your terminal will immediately flash a message saying the interface changed state to up. But for data to actually flow, the far end of that physical cable, the switch or router in the next rack over, must also be powered on and administratively enabled.
So they have to handshake.
Exactly. The two devices actually undergo a low-level physical negotiation. If the device on the other end is dead, your router's interface won't fully activate.
It's a two-way street. I also noticed in the source material that adding a text description to the interface is highly recommended.
Oh, absolutely vital. You can add a description up to 240 characters.
I imagine when you are standing in a freezing data center at 3 a.m. looking at a terrifying waterfall of yellow cables, a digital label that says main trunk to finance server is the only thing keeping you sane.
It is literally the difference between resolving an outage in 5 minutes versus 5 hours. Documentation inside the device itself is non-negotiable for professional environments.
So the lights are on and the cables are plugged in. But in IT, believing a cable works just because it clicked into place is how you bring down a whole company, right?
Trust nothing.
Right. How do we actually prove data is flowing? Here's where it gets really interesting, because diagnosing network health requires distinguishing between a quick glance and a microscopic inspection.
Let's start with a quick glance. That's an engineer's first reflex. The command is show web interface brief. It generates a clean, summarized table of every port on the router.
And what are you looking for in that table?
You are looking specifically at 2 columns, status and protocol.
Status and protocol. Okay, break down the difference, because they sound like they should mean the exact same thing.
They do sound similar, but status is the administrative state. It simply answers the question, did a human being type the no shutdown command?
Okay, so if they did, status shows us up.
Right. Protocol, however, is the physical and data link reality. It answers the question, is there a functional electrical signal negotiating with a working device on the other end of the cable?
Ah, so you could have a situation where the config is perfectly fine, but the cable was severed by a forklift.
Precisely that. In that scenario, your status would be up, but your protocol would be down. You immediately know the issue isn't your code, it's the physical environment. Both columns must be up for the interface to route traffic.
That covers the quick pulse check. But what if the link is up, the lights are green, but users are complaining that the database is just incredibly slow? How do you do a microscopic inspection?
That requires the show interface's command, which outputs a mountain of granular data. I mean, you can see the physical M-MAN-C address burned into the hardware. You see the bandwidth capacity and the delay. But the goldmine is the error counters.
What kind of errors are we looking for there?
Input and output errors, specifically things like collisions and CRC errors.
CRC.
Stands for cyclic redundancy check. When a device sends a frame of data, it runs a complex mathematical formula on all the ones and zeros and attaches the resulting number to the end of the frame.
Like a checksum.
Exactly.
Yeah.
And the receiving router runs the exact same formula. If the numbers don't match, it means the data was physically corrupted while traveling across the wire.
Corrupted by what?
Usually electromagnetic interference or a failing cable. When that happens, the router throws a CRC error and drops the packet. If you run that command and see those CRC error counters rapidly climbing, you have found the physical bottleneck choking your network.
Okay, so we can verify the health of the physical ports and the cables, but a router's actual job is making decisions. It's a traffic cop. It needs to know where the roads actually lead.
Right, and to map the roads, you inspect the brain of the router, which is its routing table.
How do you access that?
Via the show iproute command. This table, which is held in RAM, dictates the path for every single packet that enters the device. The moment you configure an interface with an IP address and wake it up with no shutdown, the router actively populates this table.
I know engineers look for specific letter codes in that output, specifically C and L. How does the router distinguish those?
Well, the letter codes dictate how the router learned about that particular network. A C stands for connected. This means the router is physically attached to that entire network subnet.
And the L?
An L stands for local. This is a highly specific route pointing to the router's exact IP address on that specific interface.
So it's basically saying, this is my neighborhood and this is my specific house.
Yes. Seeing C and L populating in the table is the ultimate verification that the router successfully recognizes its immediate neighborhood and is ready to route traffic.
So what does this all mean for you, the end user? The router is fully awake, the cryptographic locks are set, the physical ports are verified, and it knows its neighbors. The runner is on the track. But how does a laptop sitting on a desk 3 floors away know how to pass the baton to the router in the first place?
The entire system relies on the concept of the default gateway.
I always visualize the default gateway like passport control at an international airport.
Oh, that's a perfect way to look at it.
Right. If I am flying from Dallas to Chicago, I am staying within my own country. I don't need a passport. I just board the plane and go. But the moment I want to fly to London, leaving my local territory, I cannot bypass passport control. They are the mandated gateway to the outside world. Is that essentially what a computer's doing when it checks an IP address?
It is the exact mathematical process the computer uses. When a computer, let's say PC1, wants to send data to another machine, it compares its own IP address and subnet mask against the destination.
And if they match?
If the math shows the destination is on the exact same local network, the computer never talks to the router at all. The traffic is handled entirely locally by a layer 2 network switch using physical MC addresses. The default gateway is completely ignored.
Because you don't need a passport for a domestic flight.
Exactly. But if PC1 wants to reach a web server in another country, or even just a printer on a different subnet in the same building, its internal math realizes the destination is foreign.
It has to leave the local network.
Yes, so PC1 packages the data and fires it directly at the MC address of its default gateway. And that gateway is the IP address of our newly configured router interface.
Now, if we connect this to the bigger picture, there is a really fascinating quirk about those local network switches we just mentioned. It's a bit of a paradox, isn't it?
Oh, the switch paradox, yes. A basic layer 2 switch is designed to forward traffic locally between laptops and servers. To do that job, a switch does not actually need an IP address.
It just uses MAC addresses.
Right, it operates blindly on physical MC addresses. You can unbox a switch, plug in 20 computers, and they will immediately form a local network without you configuring a single IP address on the switch itself.
Yet, standard operating procedure dictates that we do configure an IP address and a default gateway on these switches. Why bother?
Because eventually an engineer will need to manage it.
Oh, of course.
If an administrator is sitting at headquarters and needs to securely SSH into a switch located in a remote warehouse to, say, check for those CRC errors we talked about, the switch suddenly transitions from being a transparent middleman to being an endpoint.
It needs an address so the connection can find it.
Exactly. It needs a management IP address, usually configured on a virtual interface called an SVI, so the administrator's connection request knows where to go.
Okay, that gives it an address to receive the incoming SSH connection. But why does the switch need a default gateway configured?
It comes down to asymmetric routing failure.
Meaning?
Think about the reply. The remote administrator sends the SSH login request to the switch. The switch receives it just fine. But when the switch tries to send the reply back to the administrator's screen, it looks at the destination IP and realizes, wait, this administrator's on a different network.
Right, they're not in the warehouse.
Exactly. And if the switch does not have the default gateway command configured, it doesn't know where passport control is. It has no way to route the packet off its own local subnet.
Oh, wow. So the reply just dies.
Drops into the void. And the remote administrator gets a frustrated connection timeout, even though the switch is perfectly healthy.
That is brilliant. It needs the gateway not to process the user's web traffic, but just to talk back to the boss.
Exactly. And in modern network architectures utilizing IPv6, this process is beautifully streamlined. You often don't even need to manually type the default gateway into the switch or the end user devices.
Really? How does it know?
IPv6 utilizes SLAAC. That stands for Stateless Address Auto Configuration. The router uses an ICMP-v6 router advertisement message to periodically announce to the entire network, hey, I am the gateway.
That's convenient.
Very. The switches and computers hear the announcement and configure themselves automatically.
It's like passport control, standing up, waving a giant neon sign, and handing out the paperwork automatically.
Pretty much.
We have covered incredible ground today. We took a deaf, dumb, vulnerable piece of metal and completely transformed it. We gave it an identity, locked it down tight with cryptographic hashing, secured the virtual pathways, and saved it to non-volatile memory.
We woke it up.
We woke up the physical ports, verified the physical and administrative states, and finally mapped out the exit door, explaining how hosts and switches use default gateways to reach the outside world.
It really is the microscopic, invisible foundation of everything we do online.
It really is. And to wrap up, I want to leave you, our listener, with a final thought to ponder that pushes beyond what we've discussed today. We just walk through the painstaking manual digital choreography required to bring a single router to life. The passwords, the interfaces, the verification.
It's a lot of typing.
Exactly. But imagine a hyperscale company like a major cloud provider or a global retailer that needs to deploy 10,000 routers across 50 countries this month. You cannot have humans physically typing host name and no shutdown 10,000 times without massive errors.
No, the human error rate would be disastrous.
Right. And this is driving the explosive shift towards software-defined networking and automation scripts using tools like Python and Ansible. The configurations we discussed today are still happening, but increasingly they are being executed by code, pushing perfect templates to thousands of machines simultaneously.
Automation is everything now.
So it raises a fascinating question about the future of networking. As these systems scale beyond human capacity, how long will it be until the human coach is entirely replaced by an AI script, leaving us to only manage the code that manages the machines?
That is a profound shift, and it's one that is already changing the landscape of the industry.
Thank you so much for joining us on this deep dive. We'll catch you next time.